Hey, how's it going? In this video, I'll talk about the um, sort of the problem with Q-learning and an algorithm that sort of fixes that problem by using a double estimator. And we'll discuss this paper that talks about double Q-learning, which is sort of the solution to the single estimator problem of Q-learning. So yeah, let's get into it. So if you, let's see. So the idea of Q-learning is essentially it's a temporal difference control method, right? And it's sort of the idea is to it tries to, given that a task is episodic in nature and follows the conditions of the Markov decision process, you can use temporal difference to estimate the approximate or to sort of converge to the optimal policy pi star, right? And the way you do it is, unlike using sort of the normal MDP control, you would use these TD methods such as SARSA, SARSA max, which is Q-learning, and expected SARSA. And how it's different from regular MC control is that instead of updating your Q table, your action value table at the end of each episode, it now updates it at every time step, right? And this can lead to faster convergence and generally gives you a better, due to the fact that it leads you to a faster convergence, you can basically get a better approximation early on, right? And so that's sort of the idea behind TD learning. And the problem, so although it works in theory, there is a huge problem with these SARSA algorithms. And the thing is the update rule, right? And if we consider Q-learning, you can see if you just sort of over here, when you're updating the next value, when you're updating the Q table through the current time step, right, given the current state and sort of the set of all actions, you're risking into an overestimation of the action values. And the reason why this is true is because of this sort of the update rule over here. So let me just change the highlighter so you can easily tell where my cursor is at. So if we consider the update rule over here, right? So the given that you're in a current state, you know, and to the SARSA max, sort of, you need the current state, the action that you just took, the reward that you got from that pair that you get from running that time step, and sort of the next state. And sort of the next action can be determined through the epsilon greedy policy approach. And you sort of pick the action based on your Q table, or if your epsilon is very large early on, which it would be, you're basically exploring the environment rather than exploiting it. So then it would be more of a random search. But let's say that you have a value where you're picking an action from your Q table, you're running into a risk of overestimating. And the reason for it is because of the fact that the next value, sort of the value of your Q table that's being updated is for the time step t+1, and you're looking at a time step t. But the thing is, you're updating the next value based on the sort of the TD target and the current value from your from your Q table. And both QT, right, both QT of next state and the one that you're updating for are coming from the same distribution, right? And these must be IID. They're coming from the same distribution and you're updating it for the same distribution, right? So you're performing this update of something from the same distribution and from the same function value itself, right? So it's like the classic example that a lot of engineers have used for this is consider you have sort of you're on like a mule or on a horse, and you're providing it a carrot in front of it, right? And you're sitting on top of this animal, right? And in theory, it makes sense that, you know, you provided this carrot and the horse would sort of just walk towards it. But in reality, that's not what happens. And the reason why is because as you shoot for this carrot in front of the horse, it sort of goes for it. As it starts to reach for it, the object sort of fluctuates due to gravity. And it doesn't always go in a smooth linear fashion like this. It's sort of the carrot goes and bounces around until the horse gets distracted, and this leads to sort of this overestimation and can cause huge fluctuations. And sort of when you're using DQN for environments that are much larger in sample space, and you know, especially for continuous time, you sort of run into these exploding gradients early on, which can cause huge troubles for your algorithm, for the convergence and finding the optimal policy, right? And so that's the main premise. So that's a problem of Q-learning in general, is the idea that you can sort of run into a large overestimation of your action values. And we're going to analyze the reason, which we sort of just stated, and we're getting the hypothesis and sort of give the analysis by looking at some of the results and the analysis of this paper. And this paper was published by, I guess, these guys, Haddo von Hasselt. There's another one published by DeepMind, where sort of, because I believe they were the ones who came out with DQNs, I'm not fully sure. And they have a really good paper on this, but for this video, we'll refer to this paper. Sort of the idea is that like we said, Q-learning's performance can be poor in stochastic MDPs because of large overestimations of the action values. And this is because of the fact that we're using a single unbiased estimator to update itself, right? And you can see that where it says that the single estimator method uses the maximum set of estimators as an approximation, right? And the reason why it's the maximum is because Sarso Max, also Q-learning, uses this idea of the maximum reward that you get from selecting a set of actions in the set of action space for a specific state S. And if you think about it, that's not very correct because you're running the risk of overestimations due to the fact that you're selecting the maximum. Initially, when you're selecting the maximum, you haven't really explored your space enough. So it's very biased early on. And this bias can continue to lead to fluctuating results and never really converge fully, or may take a long time to converge, right? And so that's the problem of this, of Q-learning. And sort of the solution that, you know, the solution behind it is using this, instead of using a single estimator, why not use two double estimator, right? And so the overestimation that you get from using the single estimator approach, which we looked at, you can sort of fix it to a large degree using a double estimator. And the idea is that instead of updating the next value of Q table, you know, Q of t plus 1 based on Q of t, you would now have from the same set, both IID, independent and identically distributed, you would now pick two different Q values, or sorry, two different dictionaries of the Q table, right? So two different Q tables would now be responsible in approximating one or the other, right? So what would happen is instead of just having Q, you will now have Q of A and Q of B. And so Q of B would now help in updating Q of A, and Q of A would help in updating Q of B. And so that's the sort of the algorithm behind double Q learning, which is based on two set of unbiased estimators rather than a single unbiased estimator. And if we just look at some of the results or some of the observations they found in the papers, that they're both part of the same set. And so the intersection, sort of the union of SA and SB is the whole samples, the whole set S, and their like their intersection is the kernel or the null set, right? So it's a null space, the empty set itself, right? And since they're unbiased, right? So we know that the mu of A, or the expectation of a set is an unbiased estimator. So that's the reason why these are, you know, unbiased. And so, and this is exactly what they say, like the single estimator UI, both mu of A and mu of B are unbiased if you assume that they're split in a proper manner, such as random distribution, so IID. And right, and so this is sort of the understanding behind it, is that if they are IID and they're unbiased, then the maximum expectation is just its average, right? It's average, right? And so this is like the cumulative distributive function for the double estimators, right? In discrete, you would have PDFs, or the probability density functions, and continuous, you would have CDFs, or the continuous distributive functions, right? And so that's the idea behind the double Q learning. And if we look at the algorithm behind it, which is essentially very simple to understand, right? You initialize from the same sample space two different dictionaries, one for evaluating Q table A and the other for Q of B, right? And then, you know, initially what you do is you randomly choose which one to update. Do you want to update Q of A or Q of B, right? And you do it the same way you would do it using regular single estimator rule, but instead of updating Q of A of T plus 1 based on Q of A T, you're now updating Q of A T plus 1 based on Q of B at that time step T, right? And so this sort of creates this negative bias where you're underestimating one of them to undershoot the other one, sort of to prevent from overestimation of one, you're underestimating the other one. And so this leverages this idea and performs much better and proves that the convergence of double Q learning can be met much faster with less of exploding gradient problem and the fluctuations of your Q values early on, right? And so that's the idea behind using two estimators, Q of A and Q of B. And when you use DQNs, the way you solve this is by using the fixed Q target, right? Instead of when you're using your weights, when you're using gradient descent, instead of updating it at every single time step, you sort of create this batch where you update your Q target at every n number of steps, but you update your main target at every single step. So now there's this sort of this hull, or this sort of delay in which you update your TD target. And so as soon as the main target, the main model has been updated n number of times, you then update this one, sort of to create this idea or this notion of double Q values or Q tables, and which is what is done. You sort of initially you have these Q functions, or this two Q tables, and you initialize them with the same weights early on, but then you update one, and then later on you update this one from the values that you get from this. And so this sort of undermines the overestimation problem, or the bias of Q learning. And so that's the idea behind double Q learning. And in this paper, the authors talk about how they use this approach to present this solution to different environments, such as the idea of roulette, the Russian card game, or other examples in grid world scenarios. So as you can see, using this approach, the number of steps that it took to converge the optimal policy using double Q learning is much larger than using Q learning, the single estimator solution. And sort of that's the idea. And the conclusion was that a double estimator approach to determine the value of the next state is a much better much better approximator for conversions to the optimal policy pi star than using the singular Q learning, right? And this is not the best approach in the sense that this is not, the fixation of the whole overshoot principle, but it does sometimes underestimate the action values, but it at the same time doesn't suffer from overestimation bias. The Q learning does, which is a huge thing, which prevents you from, as mentioned at least a dozen times already, from the exploding or diminishing, vanishing gradients and fluctuation of these of the values of the actions that your agent takes as the epsilon decreases and you're exploiting more, right? And so that's sort of the idea behind it. And the paper we looked at was double Q learning. So yeah, that's sort of the idea behind this video. And if you understood why Q learning can fail using the traditional methods, double Q learning is sort of the fix for it, right? And if you enjoyed this video, make sure to do whatever you feel is helpful in supporting this channel. Thanks.